speaker is Isabel Garcia Garcia from KITP Santa Barbara, and she will talk about field theory avatars of the Swampland.
Okay, so thank you to the organizers for the invitation, and especially also for bringing the conference online this year. Okay, so I'm gonna start sharing my screen. You should be able to see it now. Okay. So as you're all familiar with, the main goal of the Swampland program is to identify and understand the consistency conditions that semi-classical effective field theories need to satisfy in order to remain consistent when coupled to gravity. And the hope is that those conditions will provide a powerful discriminating tool as applied to effective field theories, and therefore allow us to distinguish between the landscape of consistent theories versus the swampland of effective field theories that cannot be UV completed into a theory of quantum gravity. So inspiration or motivation for these swampland conditions comes from two different sources. On the one hand, UV considerations such as recurring patterns observed in all string theory constructions, but also from the IR in the form of field theoretic arguments such as, for example, thought experiments involving black holes. And it will be precisely this type of IR considerations that I'm going to focus on in this talk. So what can we hope to learn about the swampland from field theory? In fact, we've already learned a lot. For instance, the requirement that gravitational anomalies must cancel in any UV complete theory is something that we can understand purely from IR consistency. And in some sense, it is the very first swampland condition. Thought experiments involving black holes provided the first source of suspicion that there cannot be global symmetries in a theory of quantum gravity, or that charge has to be quantized. And the same type of arguments also provided at least part of the early motivation for the weak gravity conjecture. Also, in this bottom-up spirit, there's been attempts at delineating this boundary between landscape and swampland from considerations such as analyticity and causality, including recently in trying to find some sort of proof of the weak gravity conjecture. So it is probably true that IR considerations alone cannot tell us the full story, but they can certainly provide a valuable source of alternative evidence, or even perhaps more importantly, intuition in favor of existing conjectures, but also potentially shed some new light on completely new aspects of the Swampland. So in this talk, I'm going to discuss two examples of what field theory can teach us about the swampland. I will first discuss theories with discrete gauge groups, in particular ZN gauge theories, and I will try to argue that an appropriate version of the weak gravity conjecture is also likely to apply to this class of theories. In the second part of the talk, that is going to be somewhat shorter, I will focus instead on a special class of abelian gauge series, and those are chiral G1s that are massive and that feature and cancel gauge anomalies below a certain scale. Okay, so let's move on to discuss discrete gauge theories and the weak gravity conjecture. So the weak gravity conjecture tells us that a U1 gauge theory that is consistently coupled to gravity must contain in the spectrum an object that is super extremal. And this statement was originally motivated by considering the decay of electrically charged black holes. So the same arguments can be applied to black holes carrying magnetic charge, and in this case, one obtains a magnetic version of the conjecture in the form of an upper bound on the cutoff scale of the theory, as given by G times and Planck. And this cutoff signals a scale at which the theory needs to be extended in order to accommodate the presence of magnetic monopoles. There are now more refined or more sophisticated versions of the magnetic weak gravity conjecture. In particular, the so-called sublattice version suggests a much more stringent cutoff, in fact, a quantum gravity cutoff, at the scales which are of order G to the 1/3 times and Planck. So aside from all the evidence supporting the conjecture, it also fits in well with the statement that there can be no global symmetries in a theory of quantum gravity. So by sending the cutoff of the theory to 0, the weak gravity conjecture precludes the possibility of recovering a global symmetry by taking the G goes to 0 limit. However, this statement about no global symmetries is expected to hold for both continuous and discrete symmetries. So we can similarly ask whether there could be a version of the weak gravity conjecture that applies for gauge theories that are discrete. So discrete gauge theories often arise as a result of spontaneous symmetry breaking. The simplest example is a U1 that is broken down to a Zn factor due to the wave of a Higgs that carries charge n. So in the Higgs phase, the U1 gauge boson becomes massive. So there is no classical long-range force in the discrete gauge theory. So although energies, the only effect of the discrete factor is to forbid interactions among the light degrees of freedom that violate the Zn factor. So in that sense, it is the same as if the symmetry was global. More importantly, the gauge version of a discrete theory also contains string solutions, okay? So in this example, these are solitonic cosmic strings. So inside the string, the U1 symmetry is restored, and they are characterized by an integer number k, which is the winding number of the scalar field. So although there is no classical force in a discrete gauge theory, we can still have long-range interactions. In particular, there are long-range interactions between electrically charged particles and strings in the form of Aharonov-Bohm scattering. So by means of Aharonov-Bohm scattering experiments, it becomes possible to measure discrete charge at long distances. So in a discrete gauge theory, discrete charge is an asymptotic observable, and this is the crucial difference between global and gauge discrete theories. In particular, this means that black holes can now carry discrete electric charge as hair. This was first discussed in this paper by Lawrence Krauss and Frank Wilczek, and in fact, this was one of the first examples of black hole quantum hair. So we can now take these black holes that carry discrete gauge charge and subject them to the same type of thought experiments that led to the weak gravity conjecture. So this was, in fact, first done by Guillaume de Valle and some of his collaborators in this series of papers, where they demand that there are no black holes left over at the end of the evaporation process that are stabilized by discrete hair. So from that requirement, they find an upper bound on the product of a mass of a particle that carries discrete charge times a cutoff scale lambda given by m Planck square on n. And this cutoff scale must correspond to a scale at which the properties of a black hole carrying discrete hair are somehow altered in a way that allows the black hole to lose all of its discrete charge. And I'll have a lot more to say about what this means in a couple of slides. But this early result is certainly very suggestive that the weak gravity conjecture or something like the weak gravity conjecture might also apply to theories with discrete gauge groups. So what I'm going to turn to now is to this work that I've done with my collaborators at UCSB, where we build on this intuition coming from black hole decay arguments and show that, in fact, the weak gravity conjecture itself, when applied to an appropriate description of a Zn gauge theory, leads us to the same type of result. And it will also clarify the meaning of this cutoff scale lambda in terms of providing a mechanism for the loss of discrete hair. So let me remind you first that there is an alternative description of a Zn gauge theory in terms of two U1 factors that are coupled through a topological term. So I'm going to call those two factors U1A and U1B. U1A is the usual one-form U1, so it has a one-form gauge potential or two-form field strength. U1B, however, has a two-form gauge field with a corresponding three-form field strength H. So the effective Lagrangian contains kinetic terms for both the U1A and the U1B factors. The U1A gauge coupling is, as usual, just some dimensionless parameter G. The gauge coupling of the U1B factor, on the other hand, which I'm calling here F, now has dimensions of mass, okay? And in this formulation of the discrete gauge theory, the integer n appears in front of this B wedge F coupling. So objects that carry electric charge under the U1A factor are point particles. Objects that carry electric charge under the U1B factor are strings. And the product of the two charges can be measured at long distances, again, by means of Aharonov-Bohm scattering. So it turns out that this description of a discrete gauge theory is dual to the low energy regime of an abelian Higgs model, where the additional U1B factor emerges out of a duality transformation on the face of the complex scalar. So in the U1 cross U1 picture, electric charge under this emerging factor corresponds to a scalar field vorticity in the abelian Higgs model. A string that carries k units of U1B charge corresponds to a cosmic string that carries k units of magnetic flux. And the dimension full scale introduced by the gauge coupling of the U1B factor corresponds to the scale of a spontaneous symmetry breaking. Now, in the U1 cross U1 picture, discrete electric charge and scalar field vorticity now correspond to two types of electric charge that can be measured at long distances. So we can ask what happens if we apply the weak gravity conjecture to both U1 factors. So as applied to U1A, it would imply that there must be electrically charged particles with mass below g times m Planck. As applied to the U1B factor, it would mean that the theory must contain a string excitations with tension smaller than f, the gauge coupling of the U1B factor, times m Planck. So if we want to interpret this in the context of an abelian Higgs UV completion, both the U1B gauge coupling and the string tension are set by the scale of a spontaneous symmetry breaking. And in order for the theory to remain perturbative, G cannot be above roughly 1/n. So in this context, these two upper bounds translate into an upper bound on the mass of electrically charged particles as given by m Planck on n, as well as an upper bound on the scale of a spontaneous symmetry breaking that must be below the gravitational scale. In particular, this implies that the product of m times the BEV must be below m Planck squared on n, which is the same result that was found earlier by the Valiant collaborators if we identify the scale lambda with the scale of a spontaneous symmetry breaking. More specifically, what we find is that the weak gravity conjecture, when applied to this dual description of a Z gauge theory, allows us to saturate but never violate the bound that was found in the context of black hole decay arguments. However, there is an additional consideration that we haven't discussed yet, which is how do black holes that carry discrete charge eventually manage to lose their discrete hair? So at least when discrete gauge theory is realized through a model of spontaneous symmetry breaking, then the effect of discrete charge on black holes can be studied through a semi-classical expansion using the standard Euclidean path integral methods. This was in fact first done in this paper by Coleman, Preskin, and Wilczek, where they argue that the leading effect of discrete charge on the properties of black holes is due to a virtual process where a cosmic string is nucleated on the horizon surface. It grows to envelop the black hole and then reannihilates at the antipodal point. So among other things, one of the effects of this is that even though there is no classical electric field outside the event horizon of a black hole that carries discrete charge, there will be a non-zero expectation value of the radial component of the electric field operator. So as the string wraps around the black hole, it generates an electric field in the radial direction that is proportional to the magnetic field inside the string. So the sign prefactor here makes sure that the effect vanishes whenever the charge of the black hole is a multiple of n. And the Hall effect is suppressed by this exponential factor, which corresponds to the tunneling rate for cosmic string nucleation. So for example, in the limit where the string is very thin, this exponent is just given by the horizon area times the string tension. So for very large black holes, this factor will be very large, and therefore the overall effect is very exponentially suppressed. However, as the black hole gets smaller, the effect of discrete charge becomes more important. For some black hole radius set by the scale of a spontaneous symmetry breaking, this semi-classical expansion breaks down and the effect of discrete charge becomes potentially unsuppressed. In particular, this allows for a potentially large electric field outside the event horizon. and therefore provides a mechanism for the black hole to lose its discrete hair in the same way that the Reisner-Nordstrom black hole loses charge. So in principle, by a combination of both sugar pair production as well as asymmetric Hawking evaporation. So let me briefly just summarize what I've said up to now. If we apply the weak gravity conjecture to the dual description of a Z gauge theory, what we find is consistent with previous black hole decay arguments, as well as with our understanding of the effect of discrete hair on black holes. And looking at how the black hole loses its discrete charge also clarifies why the weak gravity conjecture needs to be applied to both U1 factors. So as applied to the U1A factor, it implies that there are light charge, electrically charged particles, which makes the decay kinematically possible. Whereas as applied to the U1B factor, it implies that there are strings with low tension, which is necessary in order to generate this non-zero electric field outside of the event horizon, which in turn provides a mechanism through which discrete charge can be lost. Let me now turn briefly to the second topic that I want to discuss, related to chiral U1s and massive vectors. So there are many features of abelian gauge theories that make them very different from their non-abelian counterparts. And another example of that is what happens in the case of massive gauge theories. So in massive Young-Mills, we know that the theory has a finite cutoff, which is given by the scale of the massive gauge bosons over the non-abelian gauge coupling. So in other words, up to a factor of G, the massive vectors cannot appear below the scale of symmetry breaking. A massive U1, however, so long as it is coupled to a conserved current, it is fully normalizable. And in this case, the vector mass and the typical size of the gauge coupling are free parameters of the theory. So an easy way to see this is if we start with an abelian Higgs model. So in this case, the theory does have a finite cutoff, which is the scale at which the radial mode appears, which is given by the vector mass over the charge carried by the Higgs field. So by taking this Higgs charge to be tiny, I can, at least in principle, make this cutoff to be as high as I want. In particular, unlike what happens for non-abelian gauge theories, this allows me to have a massive vector that is as far below the scale of a spontaneous symmetry breaking as I want, so long as I'm willing to have a large hierarchy of charges between the unit of charge carried by the Higgs and the typical gauge coupling present in the low energy theory. So this is an easy way to see that, oops, sorry. Okay, now we're back to full screen. So this is an easy way to see that there cannot be a model independent upper bound on the cutoff of a massive U1. But it also highlights how parametrically light vectors are suspect, in that it requires making use of precisely those tricks that are available to abelian gauge theories that we believe are not legal or should not be legal in the context of a fully complete theory of quantum gravity. So this raises the question of whether very light vectors in fact belong in the swampland. And by very light, again, I mean well below the scale related to whatever dynamical mechanism is responsible for generating the vector mass, up to a factor of the gauge coupling that is present in the low energy theory. So this question was precisely the topic of this paper by Matt Rees, where he focuses on a class of massive U1s, which are common in string theory, which are theories with a Stuckover mass. And by a Stuckover mass, meaning that the photon mass is non-zero across the entire field space. So in this context, he suggests that one, the theory should contain a radial mode, so analogous to the radial mode of an abelian Higgs model, and that that radial mode cannot be decoupled, so it cannot be made arbitrarily heavy. And two, that the limit of a small vector mass should be singular. In particular, that there should be a quantum gravity cutoff that goes to zero in the limit of a vanishing photon mass, but that decouples as we turn off gravity. And this is motivated by the observation that the limit of a vanishing photon mass in a Stuckelberg theory requires traversing an infinite distance in field space, which, according to the Swampland distance conjecture, should not be possible, at least not for free. So these two suggestions sound perfectly reasonable. What I'm going to turn to now, that I discussed in this recent paper with two of my collaborators, is whether we can find any kind of field theoretic evidence for something like this, even just qualitatively, by looking at another class of theories where the limit of a vanishing photon mass is also singular. And these are going to be four-dimensional chiral gauge theories that are anomaly free, but for which anomaly cancellation occurs due to fermions that appear at different scales, okay? So the picture just to have in mind is this. At low energies, there is a massive vector as well as a bunch of fermions that are chiral, and the charges of these fermions are such that the low energy theory has some uncancelled gauge anomalies. And then at the higher scale, there are another bunch of fermions also with chiral charges, and those charges are such that they precisely cancel the anomalies of the low energy theory. So the full theory is anomaly free, but the effective theory below the scale of the heavy fermions is anomalous. So the results of our paper that I'm going to discuss in a minute apply to the anomaly free theory. But before I do that, before I move on to that, let me remind you about some features of the anomalous CFTs, which will clarify why these are interesting theories to look at. So we've known for a long time that it is okay for a gauge theory to be anomalous, so long as the corresponding gauge bosons are massive and that the theory comes with a finite cutoff. So for example, a U1 gauge theory that has a mixed gravitational anomaly, the presence of the anomaly implies an upper bound on the cutoff as given by this expression. So notice it vanishes in the limit of a massless photon, okay? But it decouples indeed in the limit where we turn off gravity. And this scale is a scale below which the theory needs to be UV completed into a theory that is anomaly free. Okay, so if this anomaly free UV completion is still in 4 dimensions, then this will be an upper bound on the mass of additional chiral fermions. So this is a picture of what I just said. A U1 gauge theory with a gravitational anomaly needs to be UV completed below a finite cutoff, which this is this orange line here. And here in this picture, I'm just plotting this as a function of the typical gauge coupling of the anomalous low energy theory. Notice in particular, theories that remain anomalous at the scales above this line, so theories that live in this orange region here, those theories are consistent non-gravitational effective field theories that will not remain consistent in the presence of gravity. So in this mild field theoretic sense, if you want, this class of effective field theories provide a sort of toy model of a boundary into the swampland. More generally, an anomalous U1 gauge theory might also have a U1 cube anomaly. So the presence of a U1 cube anomaly implies a cutoff scale of its own, which depending on the size of the gauge coupling might be above or below the cutoff implied by the gravitational anomaly. So this is all I'm going to say about anomalous CFTs. Let me now move on to what we find when we cancel the anomalies of the low energy theory by adding some heavy fermions. So number one result is that, in fact, this series must contain a radial mode, and that radial mode cannot be decoupled. And this is a consequence of the presence of massive fermions that have chiral charges. So specifically, if we look at fermion anti-fermion scattering or annihilation rather into a number of longitudinal vectors, we find that perturbation theory breaks down at a certain scale, and that scale gives an upper bound on the mass of the radial mode. So the expression for that upper bound looks something like this, okay? So this expression is valid when there are n species of massive fermions, all of which have roughly the same mass mf, and G left and G right here correspond to the gauge couplings between the massive vector and the left-handed and right-handed fermion currents, okay? Which by definition are different because we're considering chiral fermions. So this cutoff scale decouples in the limit where the fermions become massless, as we would expect, but it decouples only logarithmically. So unless these massive fermions are exponentially light, then this log is just going to be some order 1 correction that I'm going to ignore. And the mass of the radial mode is just basically bounded by this factor. We can turn this expression around and we see that in this series, there is a lower bound on the vector mass that is determined by the scale of the radial mode and the chiral gauge couplings. So as anticipated, we cannot have a massless vector in this class of theories, in this class of chiral gauge theories, but in principle, we can still make the photon parametrically light if we are willing to introduce a large hierarchy of charges between the typical size of the gauge coupling at low energies and the actual, what would be the actual quantum of electric charge. However, if the low energy theory has a mixed gravitational anomaly, the trace over the charges of the massive fermions must exactly cancel the anomaly of the low energy EFT. So if we introduce one or an order 1 number of massive fermion species, then it is in fact not possible to realize a large ratio of charges. It is only possible to introduce a large ratio of charges while at the same time canceling the gravitational anomaly if we introduce an equally large number of massive fermion species. So it is possible in these type of theories to have a parametrically light vector, but it comes at the cost of a quantum gravity scale that is parametrically below m Planck. So this is a picture of what I've just said. If we introduce a large number of fermion species, we can realize a parametrically light vector, but only at the cost of lowering the quantum gravity cutoff. In fact, there is a maximum value of n, which is when these two scales meet. When this happens, it turns out that these two scales are parametrically identical to this other scale, lambda gravity, which, if you remember from our previous discussion, is the scale at which the anomalous effective field theory had to be extended into an anomaly-free theory. So even if we try to push the UV completion of the anomalous EFT to higher and higher scales, it turns out it is never possible to fall into the swampland of theories that remain anomalous above this scale. So the theory itself precludes that possibility by correspondingly lowering the quantum gravity cutoff. So there is a very interesting story too that I don't have time to discuss now, when the theory also contains a U1 cube anomaly. So in this case, there is a range of values of the gauge coupling for which, as I've just said, then when we try to push the cutoff of the anomalous CFT as high as possible, then the quantum gravity scale comes down to roughly the same scale, which is this region here. But then for larger values of G, the quantum gravity cutoff has a different behavior. And in particular, it follows the scale G times m Planck, which perhaps coincidence, perhaps not, corresponds to what will be the scale of the weak gravity conjecture. Okay, so let me wrap this up. We've learned that in chiral U1 gauge theories that have a mixed gravitational anomaly at low energies, then the limit of a tiny vector mass comes at the cost of lowering the quantum gravity scale. So some of our results certainly resonate with the suggestions that were made in this paper, and I think it would be quite interesting to look more into the similarities between the class of theories that I've been talking about here. So these chiral U1 theories in 4D, and theories that have Stuckelberg photon masses. In particular, anomalous U1s are also a common occurrence in string theory. However, there are possibilities for anomaly cancellation in dimensions higher than 4 that are different from just introducing some heavy fermions. And I think it would be quite interesting to look at other anomaly cancellation mechanisms and see how the story that I've presented here changes or doesn't change. Okay, so all in all, I hope you think that there are potentially a lot of interesting things that we can learn about the swampland from a bottom-up approach. I think both discrete gauge theories and theories with U1 or mixed gravitational anomalies are promising candidates for teaching us some new and perhaps surprising things. And I think just more generally, the unusual properties of abelian gauge theories. So the fact that things like charge quantization are not built into the theory, or that in principle we can take arbitrarily large ratios of U1 charges. I think these properties make abelian gauge theories either continuous or discrete, a potentially fruitful target for this kind of approach. So thank you.
Great. Thank you very much, Isabel. It was perfect timing. And the talk was very nice also. So, so now there's time for questions, plenty of time. I have seen Miguel Montero has been raising his hand for a while, so he may be tired. So, Miguel?
Yeah, thanks, Fernando. And thanks, Isabel, for the talk. That's pretty nice. So, okay, it's probably a dumb question, but I don't, when you talk about the chiral U1s, the second part of the talk, how do I mean, in some cases you can actually fix the anomaly at the cutoff scale by introducing 1 or 2 light fields, which get a mass by coupling from the Higgs, but above the Higgsing scale they become sort of massless. So that wouldn't be. I guess that you can fix the thing with just a finite number of light fields within field theory. So I guess I didn't get why it has to be quantum gravity cutoff.
So let me perhaps go back to that slide. Let me share my screen again. Wait a second. So what I said is, wait. So what I said here is you can introduce an order 1 number of heavy fermions to cancel the anomaly of the low energy theory, okay? But if you do that, then solving the anomaly cancellation equation doesn't allow you to introduce, doesn't allow you to realize, if you want, a large hierarchy of charges, okay? That is required in order to obtain a parametrically light vector, okay? What I'm saying is that, so a parametrically light vector requires that the theory has, in some sense, a large hierarchy of charges, or U1 charges. And if I want to realize this limit while at the same time canceling the gravitational anomaly, the only way to do this, by the way this 2-term scale, is if I introduce an equally large number n of massive fermion species. In fact, the number of species is parametrically just given by, it has to be as large as the ratio of charges that I want to introduce in the theory. So
okay.
It's not motivated by just canceling the gravitational anomaly. I want to cancel the anomaly, but I want to realize the limit of a very tiny vector, which is in some sense pathological. And the point is, it is precisely pathological in the sense, right? And like
right.
The quantum gravity cutoff sort of realizes that explicitly by lowering the quantum gravity scale by demanding this large number of species. Does that make sense?
Yeah, it does. Thanks.
Okay.
Good. Okay. There's another question. I think Ling Li.
Oh, sorry. I think I must have clicked the wrong button. I just meant to clap earlier when Isabel.
Oh, you meant to clap. Okay, it's okay. Yeah, for those of you who are not familiar with this, in the participants icon, there is the option of raise hand. Otherwise, send a message in the chat if you want to ask a question. So in the meantime, I think we still have some time. Let me ask a couple of naive questions, simple questions. At the beginning of your talk, you mentioned that about the global symmetries being a conjecture. And you may compare the continuous and the discrete ones. For the continuous case, we had the old paper of Banks and Dixon. Is it for the discrete? Is it the Harlow-Guri paper is the one that covers it, or is still a conjecture?
Well, so I think the paper of Banks and Seiberg, I think I would say, that's perhaps like the first paper that also, talks about how, having global discrete symmetries is potentially sort of pathological. But it's true that, the Harlow-Guri paper that proves these statements, at least in, under certain assumptions, their results apply to both continuous and discrete symmetries.
Mm-hmm. So
and I think that is further evidence that.
But why is it still a conjecture and not a result?
Well, I mean, so I think, it is partly established, but I wouldn't say that it has been established, in full generality, right? Like, there is a proof within certain assumptions using ADS-CFT. Maybe that's just like settled for you, but I would say like there are perhaps other theories, right, that are not necessarily holographic, and in those cases, we still quite don't know. It's not like I'm trying to. It is partly established, and I'm happy to call it a proof, but okay.
Okay. Okay, maybe I saw Eros in the audience. Maybe he may want to comment at some point. But in the meantime, I have a second question. In the second part of your talk, did you consider at all the Green-Schwarz term that cancels the anomaly for the?
Right. So what I said at the very end of the talk that there are other possibilities for anomaly cancellation when the theory is not UV completed in 4D. That's exactly what I had in mind. But we didn't look at this in our paper. So we just focus on 4-dimensional UV completions. And in that case, you are just stuck with having massive fermions. But I think it would be, one of the most interesting things to do would be to see what happens when the anomaly is UV completed into, by using a different, again, like Green-Schwarz or something in higher dimensions, and see, what bits of this story sort of stand and what changes. Indeed.
Okay, thank you. I can see Jonathan Hetman has a question. He typed it, but maybe you can talk, Jonathan. It may be better just say it directly.
I can just say it again. So you talked about a ZN type bound. So you had a Swampland type bound in the case of discrete group ZN, which involved the order of the group ZN. Can you comment on possible generalizations involving products of cyclic groups or non-abelian discrete groups? So how does it depend on order of group or representations of those groups in the more general case?
I think that's a great question. That's not something I thought about. So my focus on the ZN case is twofold. For one thing, it is the simplest case, but also, this bound that involves the product of, the mass of some particle times the cutoff. If you remember, it goes like n Planck squared on n. So, that goes to 0 as you take n very large. So as you take n to infinity, you will recover a global U1, and sort of, this bound kind of stops you from doing this, at least for free. So, that was like that is a nice way to tie these statements about the discrete theory with the no global symmetry statement. There are, of course, also, as you say, non-abelian discrete gauge theories. For those, it is a little bit more difficult to see how you could realize something like that, and I just haven't thought about it. Like, I just haven't thought about theories with non-abelian discrete group. But I think in the spirit of what I said, I think discrete gauge theories are actually, they are common also in a string theory, arise generally as a result of spontaneous symmetry breaking. And I think there's probably a lot more to learn about discrete gauge theories, both abelian and non-abelian.
Thanks.
Okay. So we have, I don't see any other hand raised and no chat. Kumrun, you have a question?
Yes, is there any bound that you can get on the order of the groups? Because we expect the bound, is there a field theory connection with the order being too big? We don't have, all the string examples, we don't seem to go beyond such an amount, but we don't have a universal statement. Do you have any ideas from field theory that might guide us?
So, I mean, I still cannot make a universal statement, but I think I would say it's encouraging that, from this bound that was already actually extracted from this black hole decay arguments from the Valley and company, n times the cutoff has to be smaller than 10 Planck squared on n. So you at least see that, taking n very large comes at a price. I cannot just from field theory sort of give you like an upper bound on n. And I think to me, actually, that is one of the most interesting open questions, like how large can n be from some kind of first principles? Because it's also one of the things that will have the most impact for how all these conjectures affect phenomenology, right? Which, I mean, like all these loopholes that come up are always related to these things. Like in U1s, we can take n to be large in principle. Like we don't have a fundamental bound on this number. Yeah, so I cannot tell you anything in this respect.
Okay, well, thank you very much, Isabel. So we can all clap by ourselves, and thank you, Isabel, for the nice talk. So before we go to the next speaker, I think Jim has another announcement to make. Jim?
I'm sure.